This is an event conducted by the IEEE PES ASU student chapter. Today we're hosting Dr. Eirini Eleni Tsiropoulou. She's an an associate professor in the School of Electrical and and Energy Engineering at ASU. She earned her PhD from the National Technical University of Athens, and her research focuses on game theory and reinforcement learning for decision making in complex systems. She is also the recipient of multiple Best Paper awards and has been recognized as a top 10 rising star by the IEEE N2 Women. Her work is supported by the Department of Energy, NSF, and Industry. She also serves as an editor for several IEEE journals and co-chairs the N2 Women community. Over to you. Thank you for doing this, Professor.
Thank you, Niru. Pleasure to be with all of you. Can someone confirm that you can see the share screen?
We can.
Excellent. So a real pleasure being with you today. It's actually my first talk in an IEEE student branch here at ASU. So I'm really happy about that. I appreciate the kind introduction. So let me give a little bit of background before we start this talk. So the lab is working in several decision-making problems in complex environments. And one of those environments are the renewable energy resources, where we mainly focus on concentrated solar power fields. And when I say decision-making in complex environments, the decision-making can be related to allocation of resources, to cybersecurity, to optimize the operation of the complex system, not only making it secure, but also robust and also modular in its operation. We have other fields in the lab that we are working on, and they span all the way from wireless networks to cybersecurity, to edge computing and cloud computing, social networks, and also AI systems for intelligent decision-making. So today the talk will focus on the solar energy systems and how we can design an AI-enabled system, an artificial intelligence-enabled system, building on the software-defined networks concepts in order to support the wireless communications in concentrated solar power fields, but also make them secure and make them adaptable to different conditions in the environment while they operate. And I will dive directly into the details. Let's understand, first of all, how our interest came to the concentrated solar power fields. So nowadays we have different types of renewable energy systems, and mainly the way that they are controlled is based on rigid architectures, that they are mainly hardware dependent. So we deploy the hardware in the field, either if those fields are photovoltaic fields or concentrated solar power fields. So we have quite a lot of challenges related to their scalability, but also their real-time adaptation to changing conditions of the environment, but also changing needs of the field. Also, the existing control systems in those energy fields, like, as I said, photovoltaics and concentrated solar power fields, they have major challenges in terms of how they can manage the dynamic operational requirements. So such an energy field may have different needs day to day. So for example, adapting to the real-time energy need of the grid or adapting to the real environmental conditions in the field. Now, how our interest went to the wireless communications in those fields, we observed that the majority of the existing deployed already energy systems, they are mainly controlled in a wired manner. So the commands that are sent in the field are being communicated over a wired communication network, which has several drawbacks. And the main drawbacks is mainly the high installation cost, but also the high maintenance cost. But obviously it has some benefits, which is practically its stability and its security in terms of operation in different environments. Because obviously the wired communication system is more robust to the stochasticity of the environment, that the stochasticity is more dominant in a wireless communication system. But also this wired communication environment, even though it has those benefits and those drawbacks that we discussed, it has several also scalability issues, given that the wire is quite costly. When we discuss about large-scale energy systems, the cost for the wired communication becomes quite prohibiting, especially when we discuss about concentrated solar power fields, where we have tens of thousands of heliostats being connected to a central controller. So we target in designing a sustainable solution where we exploit the wireless networks in concentrated solar power fields in order to make sure that they are robust, they are controllable, and they can adapt in a real-time manner to the environmental conditions, but also to security threats within the system. And why we are so much interested in the CSP technology, I guess it is not a secret that the need for energy nowadays is increasing. So we try to introduce robust renewable solutions that they can supplement the energy availability within the market. And one solution that is relatively free, and I say relatively because it comes also with the cost of installation and operation, is the solar energy. Now, the wireless technology, it can revolutionize the solar farm operations because it can decrease substantially the cost. It can provide scalability within the system because we don't need all those wires within the field. And also it can provide adaptability because we can, in a software-based manner, control the system and also monitor its operation in a real-time manner. So now the wireless solution, however, it comes with some challenges of how it should be integrated within the environment in order to minimize the environmental footprint. But obviously, the wireless devices are very low energy devices that even they can operate in a fully autonomous manner by attaching a small photovoltaic to the wireless nodes. And this is practically what we try to envision in this talk that I'm going through. So now, for those who are not very familiar with the concentrated solar power field technology, it's very similar to the concept of photovoltaics, at least how they look like. So it's fields of mirrors, thousands of mirrors, that instead of absorbing the energy from the sun, they reflect the sun to a tall tower where we can heat a liquid, and from the thermal energy we can create electricity. So the concentrated solar power fields are very popular in countries where the direct normal irradiance is quite high, and practically in simple words, that means how direct is the sunlight to those mirrors. And typically those areas are, for example, in our area, like Arizona, so all this southwest belt in the United States, and obviously South America, Africa. This technology is very popular in countries like Israel, and China is also leading this technology, but also in Europe, in Spain. So it's a technology quite well known out there. We have one very large field, the Ivampa field in Nevada, at the boundaries of Nevada and California, where this field is operational, and it consists of 350,000 mirrors and 3 towers in order to collect the energy. Now, to start diving into more in the details, like why the wireless technology can substitute or even supplement in the worst case scenario, the wired communication, we need to understand the cost analysis and the benefits of the wireless technology. So in this table, I have highlighted mainly the differences between the wired and wireless technology, where obviously the cost for the wired technology is quite higher than the wireless one. And some indicative figures, the cost for just installing the cabling related to just one heliostat of a size of 20 square meters is about $400 per heliostat, While if we substitute all this wired communication with a wireless module that has attached a small photovoltaic, so it can be self-sustained while it is in the field, the cost comes about to $100 per heliostat. And this is just for the installation cost. The cost can be further decreased if we consider also the maintenance cost, which in the cabling case, it's much higher. So based on those numbers, if we examine our example here in the US, the CSP field at Tivampa, as I said, it has about 350,000 heliostats, and the cost just to install the wired communication within the field and reach out at every heliostat, it would be about 140 million based on the figures that we discussed earlier, while this cost can be reduced by 75% by using the wireless technology down to the 35 million. And as I said, the maintenance is a major issue for the wired communications, as the cables, obviously, they wear over the time, so, and also they can be damaged because of the weather. So this impact is much more negligible, I should say, in the wireless technology. Now, one other major difference comes to the scalability. So when we discuss about those very large fields that they have radius of kilometers and all those thousands of heliostats, obviously cabling the whole field, it's quite expensive. And also difficult to scale, and also difficult to scale, given that you need to trench the whole field. This does not hold true in the wireless technology, given that the wireless module is attached on the heliostat, so there is no need for cabling or further operations within the field, which they are not only costly, but also they may be difficult to be performed in a real field. Now, I should highlight, though, that the wired communications are very stable, given that they are not affected by the wireless conditions. So when we discuss about the wireless technology substituting the wired communication, we want to make sure that the system that we design is robust and it is secure, and it can operate in the field without practically losing data while the heliostats are communicating with the central station that sends the control commands. Also, I should highlight, related to the reliability of the operation of the field, that if the field goes down because of loss of communication with the central station, the cost is not negligible at all. So we want to make sure that the communication system that we design, in order the central station to send commands to the heliostats, it needs to be extremely reliable. Now, the solution that we propose here, considering the existing challenge of managing such a complex system with thousands of connected entities, we want to make this system reliable and we want to optimize its operation, is how we can design such a system, how we can trust the wireless communications, that the central station can always control the heliostats in the field. So to do that, we introduce a software-centric model where practically it goes away from the rigid concept of hardware-oriented solution, and we practically softwareize our solution by using network function virtualization, where we virtualize in a network function level the main tasks that they need to be performed in the field, like routing and spectrum management within the wireless communications. But also, as I said, we softwareize the solution by utilizing SDN, software-defined networking concepts, where practically the central station can orchestrate in a centralized manner the commands that they need to be sent to the nodes, and then the nodes, considering those commands, they can operate in a fully decentralized manner. So the situation is quite mirrored. So if we want to envision how we are deploying this NFV and SDN convergence, so how we have the virtualization of the network functions, being translated in a software-defined networking environment in order for the field to operate, we go away from the, as I said, the rigid hardware-oriented solution, where in this solution, practically existing implementations, even wireless implementations that have been introduced in the field are using access points and routers deployed in the field. And we go in a higher layer where we are implementing a central SDN controller at the central station, where practically commands like routing, management, dynamic spectrum management in the field can be translated in virtual network functions at the central station, who can centrally determine those optimal solutions and then broadcast them to the heliostats, and then the heliostats can operate in a fully decentralized manner by utilizing a simpler hardware plane at the field, which also can reduce the cost. So our proposed solution is called Heliocom. It's a patented solution available out there. And the main idea is that it introduces the wireless communications within the concentrated solar power fields by utilizing software-defined principles. So in those principles, what we can implement is practically the dynamic spectrum management, where the field is sliced, is divided in different frequency zones. And then on top of that, we are implementing a dynamic clustering, where the clustering is performed among nodes that they belong within the same frequency zone. So practically, in simple words, the nodes can talk in the same language, meaning the same frequency, but also within the clustering, we are introducing the concept of non-orthogonal multiple access technique and successive interference cancellation technique at the receiver, which is a novel method in order to deal with the very high interference levels that they exist in a field of thousands of connected wireless nodes, where practically the nodes, they can use the same resource in order to transmit their data, but there is an intelligent successive interference cancellation technique performed at the receiver in order practically to have the lowest packet error rate possible within the field in order to decode your data and not fall into the drawback of continuous retransmissions in order for the data to be reported. And then after we have those frequency zones, we have the clusters. We implement also an interference-aware routing. So each node, each heliostat knows which route it should follow within the field in order to report its data to the central station. And on top of that also, given that we have a hierarchical network, so we have the clusters have some cluster nodes and one cluster head, and then the cluster heads communicate among each other through the interference-aware routing in a wireless also manner, so the whole field is fully wireless. We are using the integrated access and backhaul technology, which on top of the frequency zones, it allows us to dynamically allocate the spectrum between the access network and the backhaul network. So practically, we can allocate the spectrum at the area that is more needed in an intelligent manner. So what is our vision with this proposed solution is practically that we want to introduce this software-defined backbone within the concentrated solar power fields in order to enable their self-optimization and make practically the energy ecosystem that we are studying intelligent enough to adapt to the real-time conditions that they can be changing over time in an intelligent, obviously, manner. And intelligence means that we want to make sure that the system operates in a reliable manner. So to start diving into the details, here you can see a picture of a very large CSP field. It's more than 44,000 connected heliostats. And you can see in the field the frequency zones that I explained earlier. They are the different colors. And then you can see the clustering mechanism that is performed between zones of the same frequency. And then after the clusters are created, the cluster heads are performing the interference-aware routing in order to communicate the information all the way to the central station that it's at the bottom of the field if you see my mouse. So in the HelioCom solution, each heliostat is equipped with a wireless module. The wireless module also has attached one small photovoltaic, and we have this testbed available here at our lab, at Proton Lab, here at ASU. And each node practically communicates in a wireless manner. The cluster, the access nodes communicate to the cluster head. The cluster head practically acts as a local coordinator. It collects all the information from its cluster, and then in a wireless manner, multi-hop communication, through other cluster heads, it reports the information to the central station, where practically the central station is practically the brain of the whole field, where operations like routing, like dynamic spectrum management, clustering are performed there and then broadcasted to the nodes. Now, the challenge, as I said earlier, it's the scalability in those fields. So when we initiated, this framework and this solution, when we initially patented it, we started testing in small-scale fields, like about 7,000 heliostats. But the problem of interference becomes quite challenging in the wireless medium when we scale up to tens of thousands of heliostats, as are many real CSP fields out there. As I gave the example earlier, EVAMPA has 350,000 heliostats. So there is an existing challenge about the scalability. So obviously, if we just had a point-to-point communication in the field, obviously this wouldn't scale. And this is the reason that we need this hierarchy of the clusters. So we have, as you see in the figure, we have the cluster nodes communicating to the cluster head, and then the cluster heads communicate among each other all the way to the central station. Now, the clustering practically is based in an intelligent method that accounts for the interference in the field and the spatial diversity of the nodes within the field. And in a real CSP field, two main operations take place: the closed loop autocalibration and the non-closed loop autocalibration of the heliostats. In the closed loop autocalibration, to describe that in simple words, a batch of heliostats is practically reporting every 250 milliseconds information with the central station in order to auto-calibrate where the heliostat points and optimize its angle in terms of pointing to the central station, so we can maximize the energy harvesting. So then on the other hand, the non-closed loop autocalibration, it's just regular commands that the central station wants to send to the nodes. So they are, let's say, of less priority and lower latency constraint. So as you understand, in our system, obviously the nodes that they are performing CLA operation, closed loop autocalibration, they are the most critical because we want to auto-calibrate the heliostats to maximize our energy harvesting. So the way that we are performing the clustering is first we cluster the CLA nodes, and then we cluster the NCLA nodes under the condition that the non-orthogonal multiple access technique and the successive interference cancellation technique are respected, which, if I want to describe that in layman words, that means that when we add heliostats within the same cluster, then the heliostats that belong in the same cluster need to have clearly differentiated strength in the received signal power. So practically the head, when it receives, let's say in this example, those three signals, it can understand and decode the signal from each one of them, given that the signals are coming in a superposition manner because they are using the same medium, the same spectrum band. So we first cluster the CLA nodes, and then we follow with the clustering of the NCLA nodes, by making sure that we respect the decoding of all the information within the field, considering the previous clusters. So with that, this is practically a simple description of how our clustering approach works, and the intelligence practically comes on exploiting the spatial diversity and the signal strength of the nodes within the field. Now, after the clustering is performed, we are utilizing a low complexity game theoretic approach in order to determine the optimal transmission power of each node within the field, but also the optimal allocation of the spectrum between the access network and the backhaul network among the cluster heads to communicate with the central station. This problem is formulated as a non-cooperative game theoretic problem, where practically the heliostats are the agents, the players within the game, and the goal is to determine their optimal transmission power, and an additional goal for the cluster heads is to determine the bandwidth splitting in order to implement the integrated access and backhaul technology that we discussed earlier. And how they determine those three variables within the system, considering that the ultimate goal is to maximize the energy efficiency and also maximize the data rate that they achieve within the system. We determine a Nash equilibrium, so we know that the system is stable while it operates. Now, some indicative results from our experiments. We have initially tested a relatively small scale topology with about 7,600 heliostats in the field. And the first thing that we were interested in was what is the latency? What's the communication latency? So at the bottom graph, you can see what is the latency for the closed loop autocalibration heliostats. Our experiments span a duration of 2 years, from January 2020 to December 2021. And I want to clarify that those are mainly simulations based on real data sets that we have. So we can practically test how the system behaves in a 2 years duration. And at the top graph, you can see the corresponding maximum latency for the heliostats that are performing non-closed loop autocalibration. So our major findings is that for the critical heliostats, the ones that they need to be auto-calibrated in the field, we respect the 250 milliseconds latency, as you can see here, while for the, let's say, less critical heliostats in the field that they are receiving regular commands, we stay below the 2 seconds. Now, the reason that you see those zigzags in the graphs are practically mainly stemming from the channel gain conditions within the field, because the heliostats are moving in a real-time manner during the year, actually during the day, and obviously during the year. So the channel gain conditions change. Also, you should consider that the channel gain conditions change also due to the weather conditions. And that's why you see some abnormal, I wouldn't call them abnormalities, actually they are normal, but you can see those zigzags within the graph. Then we also studied what is the energy efficiency, and the energy efficiency is practically defined as the megabps per joule, actually megabits per joule. So it's practically a data rate over the corresponding power consumption. And we have respective results for the CLA and the NCLA operation. And what we have observed is practically that the system that we have designed, it can ensure a minimal environmental footprint based on the proposed solution. Now, we compared our results. Our results is practically the clustering results, as compared to having a simplistic segmentation of the field instead of this intelligent clustering that I presented earlier. And we wanted to observe how that affects the data rate, meaning how fast the data are being transmitted within the network. And what we observed is practically that the intelligent clustering based on AI and on an intelligent AI approach that we have introduced, complemented also by the resource allocation mechanism that I discussed earlier with a game theoretic approach. It can practically achieve high data rates within the field, even in those dense environments of almost 10,000 heliostats, 7,600. Now, another topic that I want to extend our discussion today is how the system is practically affected during the year. So there are some seasonal dynamics that they can affect the operation of our solution and actually the operation of a real CSP field. And why so? So if you see on the graph on the right of the slide, you most probably are familiar that the sun has different positions during the year, and obviously the path of the sun changes between the summer solstice and the winter solstice. So practically how vertical the sun is as compared to the heliostats that they need to point to the central station, it changes during the year. So we wanted to observe this real environmental factor, how it can affect the operation of the field. And for the CSP engineers, it is very critical to make sure that they can auto-calibrate the field in order to maximize the energy harvesting at the central station. So that means that they don't want to have heliostats that they point in a completely wrong direction, so which practically that will result in loss of energy. So we need to make sure that the system, the control system that we design in terms of communicating with the heliostats, it can support the closed loop auto-calibration during the year. So our experiments focused on how long it takes for a CSP engineer to control and auto-calibrate the field. So we ran experiments for the 4 different seasons during the year. Practically, the seasons are defined by the corresponding 3 months. And we wanted to see what is the impact of the sun's position within the auto-calibration of the field and how long it takes to auto-calibrate the field. So here the results are showing that for a large-scale field, the duration of the closed-loop auto-calibration is relatively higher during the winter, and it presents very similar behavior during the spring, the summer, and the fall period, which practically this can be an information that the CSP engineer should consider in order to determine also how long, in order to know actually how long it will take to auto-calibrate the whole field in order to optimize the energy harvest. But also we studied how it affects the latency of the cluster heads at the top graph and the access heliostats. And here we present practically the average results for a 1-year duration. And what we observed is that the latency remains relatively low, given that we have a consistently low packet drop ratio within the field during the year. And we observe that the latency is even lower during the, let's say, more sunny months, and obviously this holds true given the movement of the heliostats during the corresponding period. Now, I want in this talk also to expand our discussion in an additional angle in this field, which is practically the cybersecurity within the field. So when we design a complex system, we care obviously to be reliable, and it's whatever we discussed so far, but also to be secure. So how we secure this field, we need to study different potential security attacks, and what is our methodology, first of all, to detect those attacks, but also to eject those attacks. So our initial efforts have focused on jamming attacks. The jamming attacks are practically attacks that they try to increase the transmission power level of the heliostat nodes in order to increase the interference within the field and ultimately prohibit the communication of the heliostats with the central station. If this happens, a heliostat is not controlled within the field, which someone can say, okay, I can lose part of the energy that is harvested from this heliostat, but the attack can become even more dangerous because if you lose control over a heliostat or a batch of heliostats, then someone else can take control over those heliostats and point to the central tower, and an increased level of heat can even burn the tower and destroy the whole field. So the damage that can stem from a jamming attack can be just losing some energy, and I say the word just within many quotes, but also it can go all the way to destroying the whole CSP field. So let's see what is a method that we have invented in order to detect those attacks, but then also to eject those attacks. So our method practically exploits the over-the-air computing technology The concept of the over-there computation practically is that when multiple nodes are transmitting data to one receiver, and you can think the cluster nodes to the cluster head heliostat, then their signals are superposed over the medium, and the cluster head practically receives a superposed signal that then it can further transmit all the way to the central station. So we utilize this concept, given the clustering that we have already within the field, in order to perform an AI-based signal analysis that mainly utilizes machine learning approaches in order to analyze the different properties that are derived out of the wireless signals. So when a signal is transmitted from one node to the receiver, there is a corresponding received signal strength, that this can be an indicator of what was the corresponding transmission power, given that those nodes within the field are static, relatively static, okay? In order to achieve this goal, we complemented our machine learning technique by the hypothesis testing, where the hypothesis testing, in simple words, what it practically checks is that if the average received signal strength at the receiver, considering some stochasticity within the system due to different noise, and considering an elasticity factor, because it doesn't mean that all the failures are attacks, it can be just an abnormality within the system. So we are using the hypothesis testing in order to detect possible misbehaving nodes within the field, which can result in a higher received signal strength, which is an indicator of a jamming attack. Then when we identify that there is a potential attack within the field, we can use triangulation techniques in order practically to detect the node from the field and isolate and eject it from the network. So some indicative results from some testing that we have performed, mainly focused on the average mean squared error within the field in order to detect the attacker within the field. And practically, this hypothesis testing that I explained earlier, it's like an intelligent watchdog. So practically, it's a condition, it's like an alarm, that if it is violated, we understand that a potential jamming attack occurs in the field. So practically, we can continuously monitor the field by analyzing the statistical distribution of the received signal strength, and then by using the hypothesis testing, we can identify and detect the node within the field. And the results that you see on the graph are practically denial of service attacks, where we have only one attacker within the field, and distributed denial of service attacks when we have multiple attackers within the field, and the scenarios are without not ejection, without ejecting the node, the attackers, or with ejecting the attackers. And obviously you can see that if we have a distributed denial of service attack within the field, the harm that it can have in the field will be substantially higher. Now, we run also some tests, again, under the concept of the single attacker, single jammer, multiple jammer, so denial of service attack or distributed denial of service attack. And we wanted to have a sensitivity analysis of how the detection threshold that we saw in the hypothesis testing affects practically the success of receiving the signals, as it can be quantified by the average mean squared error. So now, in all those tests, our goal at the end of the day is to remove the attacker. So we have detected the attacker based on the AI approach complemented with the hypothesis testing. Now we want to to eject the attacker. So in the ejection process, our solution, practically what it does, it initiates the challenge phase, where practically it has a set of nodes transmitting to the within the field, and then it analyzes practically the information that it receives through the received signal strength indicator, and then we are using triangulation in order to detect the specific location of the node within the field that is misbehaving as it is derived by its received signal strength, the concept of misbehaving. So we have performed, in order to test this solution, some detailed simulations by emulating practically the solution that the field, the National Solar Thermal Test Facility field, which is a testing field at Sandia National Labs. So we took the exact topology and we performed some testing where we implemented our whole solution, the wireless component, the whole virtualized solution with the routing, clustering, frequency zones, all the things that I discussed earlier, and the detection of the jammers. So what we observed is that our proposed solution, especially when we have one jammer, the impact can be relatively very small in terms of receiving the data accurately at the receiver. And then when we have a distributed denial of service attack, we need to very carefully consider the detection threshold in order to accurately detect the attackers within the field. And here I present a sensitivity analysis with respect to this detection threshold. And moving forward, we performed also a more thorough analysis where we considered the detection threshold, the level of the attack within the system, so how many jammers we have within the system. And I need to remind you that I think I didn't say that earlier, that the NSTTF topology at Sandia National Labs, it has 218 heliostats. So what we observed from our testing is that the proposed approach, the solution that practically exploits the hypothesis testing with the detection threshold, it can achieve a very high jamming detection rate within the testing field that we explored. And to start wrapping up what we discussed in this talk, so the main contribution of our lab in the field of CSP technology is practically the Heliocom solution. And the idea is that we combine components and ideas from artificial intelligence, wireless communications, reinforcement learning, game theory, and also cybersecurity in order to design a reliable, secure, and robust system that can adapt in a real-time manner in several dynamics that are coming into the environment, either if they are malicious or if they stem from the environment, like the seasonal dynamics, or if they stem from any abnormalities in the environment, so for example, or real-time events like the weather conditions. So why this solution is important? So the main I think contribution of this solution is it is a reliable solution that at the same time it can reduce substantially the cost, and substantially in our figures means 75% of operating in a smarter, resilient way a CSP field in real commercial fields out there. Now, we have some future research direction that we want to explore within the lab, and because this is a talk to students, some of you may be interested in engaging, especially we have several master thesis topics. So we want to extend our solution by using deep reinforcement learning approaches in order to optimize the network operation and the control of the heliostats. But also we want to study different types of attacks like spoofing and backdoor attacks, man-in-the-middle attacks. And we want to test how our solution can be can support different other hybrid renewable energy systems that combine different technologies like solar and wind. We want to perform some testing within the Proton Lab. Proton Lab has a very large facility at Mesa where we deploy this field within ASU in an outdoors environment to perform some real testing, and we have all the equipment. Now, to conclude the talk, we want to extend our solution to different other fields because practically our solution supports an industrial Internet of Things field. It's not really bounded within the CSP technology. So it can find applications in managing the distributed energy resources in smart grid and different other industrial IoT systems like smart factories, agriculture, and smart manufacturing. But also we are very much interested in applying this technology. Actually, we currently do that in the concepts of low altitude economy. That is practically a technology up and coming in the United States, where practically we are using drones for different operations within smart city but also rural environments like delivery of packages, delivery of medicine, public safety, etc., etc. So this is the list of publications that have resulted out of this solution, and also one of the available patents. There is one more that I need to update this slide, and this work is supported by the Department of Energy, and 3 of my senior PhD students are involved in this project, Sadmana, Isa, and Dipanjan. And I think with that, I will conclude the talk and I will open it for questions.